It's my great pleasure to welcome Michela Mapelli today. She is a professor in Padova, and before that she was a postdoctoral fellow at Milano Bicocca and also in Zurich. Today she's going to tell us about an area where she's been really transforming our understanding of the evolutionary history of black holes from their sort of formation, not as black holes but as stars, and their dynamical evolution in their environments up to the point where they merge and we can see them in this incredible new way through gravitational wave detections. So let's welcome Michela, and we're looking forward to your talk.
Thanks, Morgan, for this very nice introduction. So, I'm Michela, I'm from Padova, and it's really a pleasure to be here in this wonderful town during foliage season, by the way. And I already enjoyed several discussions with some of you. I'm looking forward for more, and I really would like to thank the organizers, and especially Morgan, for inviting me here. I'm super happy to be here. And today I'm going to tell you about my research on black hole demography. This is the outline of my talk. I will first briefly summarize what we learned, well, what I learned from gravitational wave detections, and I will discuss the mass of black holes and the formation channels of binary black holes in the cosmological context. In September 2015, about 4 years ago, the LIGO interferometers obtained the very first detection, direct detection of gravitational waves, GW150914. This event is associated with the merger of a binary black hole, and since the very first observation, the LIGO interferometers and then the Virgo interferometer, which joined in 2017 and is in Italy, have obtained several other observations. The LIGO-Virgo collaboration has published 10 binary black holes and 1 binary neutron star as a result of the first and second observing run. And the third run is currently ongoing. Well, right now the detectors are offline, but they will be back soon. And several new triggers were already announced during the third observing run. So these are definitely exciting times for gravitational waves and gravitational wave astronomy. And I'm an astrophysicist. I study black holes from an astrophysical perspective. And I think I can summarize, efficiently summarize what I learned from LIGO-Virgo detections with 3 sentences. Thanks to LIGO, we know that binary black holes exist, that they can merge in less than a Hubble time, and that stellar-sized black holes with a mass in excess of 20, 30 solar masses actually exist. And each of these 3 points is a crucial point for astrophysical black holes. Binary black holes exist. Theorists, astrophysicists have studied these systems for many decades before we actually got a confirmation that they exist, which W150914. They can merge in less than a Hubble time. There was a lot of skepticism about that, because for 2 black holes to merge within a Hubble time, they should start from an orbital separation that is a few times the radius of the Sun, so very, very close to each other. And third, black holes, stellar-sized black holes, can have a mass larger than 20 solar masses. This was quite a surprise for the astrophysics community, because the only black holes for which we had a reliable dynamical mass measurement when GW150914 was observed are a dozen of black holes in nearby X-ray binaries, and none of them has a mass above 20 solar masses, as you can see from these red points in this compilation. In contrast, the blue dots here are black holes in gravitational wave events, the ones reported by the LIGO collaboration, And you see that most of them have mass larger than about 20 or even 30 solar masses. And it was quite difficult even to explain the formation of these systems, because the vast majority of models of black hole formation by the time of the publication of GW 150914 did not expect the existence of these black holes, with few exceptions in the literature. For example, in 2015, few months before the detection of GW 150914, we published this plot. This was an update of our model. And here you see the expected mass of the compact object versus the 0H main sequence mass of the progenitor star of the compact object for 9 different metallicities. And you see that with this kind of model, we can account for the mass of GW 150914 and the other black holes, but only if the metallicity of the progenitor is subsolar. So in the next few slides, I will try to discuss with you what are the main physical ingredients of this kind of models and what are the many uncertainties about these models. So astrophysicists think that there are essentially two main physical processes that affect the mass of a compact object, and one is the mass evolution of the progenitor star and its core, essentially means the effect of stellar winds. And the second one is the final fate of the star. The big question is the massive star going to explode as a supernova, or is it going to collapse to a compact object directly? As to stellar winds, we have known for a long time that stars, especially massive stars, lose mass by stellar winds. In massive hot stars, stellar winds are essentially line-driven stellar winds, and the mass loss for line-driven stellar winds depends on the metallicity of the progenitor. The higher the metallicity, the stronger the mass loss. But it also depends on the luminosity of a star. The closer it gets to the Eddington luminosity, the higher the mass loss, basically regardless of the metallicity of the progenitor. And I think the simplest model that we can adopt to account for both metallicity and luminosity dependence is this one, where the mass loss m dot scales with the metallicity z to alpha, and alpha, yes, is a function of gamma, which is the Eddington ratio, the ratio of the current luminosity of the star to the Eddington luminosity. And with this kind of simple model, we can describe the mass evolution of a star like this. We start with a star of 90 solar masses, we evolve it with 7 different metallicities, from solar to very low metallicity, and while for very low metallicity the star retains most of its mass by the end of its life, this last point here is the onset of core collapse, basically, the meta-rich star loses more than half of its mass. And we think this is crucial because the mass of the star and the mass of the core of the star at the onset of collapse may have a crucial impact on the mass of the compact object. Which brings us to core collapse supernova, unfortunately. I have to say that when we talk about core collapse supernovae, I always have to say that our understanding of core collapse supernovae is quite incomplete. If you browse the literature to find prescriptions for the outcome of a supernova, you find many of those prescriptions. For example, according to Fryer and collaborators, you can kind of predict the mass of the compact object based on the carbon-oxygen mass of the star at the onset of collapse plus the final mass of the star. According to O'Connor and Ott or similar papers, you can use the compactness parameter here plus the final mass, or there are even more sophisticated models in the literature. Unfortunately, none of them is completely satisfactory, but there is quite a common feature that is common to all of these models, and it is if the final mass of the star and the final core mass of the star are quite large at the onset of collapse, then the star gets a higher chance to collapse to a black hole directly without a supernova explosion. And it's reasonable to expect that if the black hole forms from collapse rather than from an explosion, its mass will be larger. But since metal-poor stars can have larger pre-supernova mass than metal-rich ones, because stellar winds are quenched, then they are also more likely to end up their life with more massive black holes. And this is the bottom line beyond these kind of models. So there are many uncertainties about stellar evolution, about core collapse supernovae. This model comes just from one choice of stellar evolution model and core collapse supernovae, but the main feature is that from the interplay between direct collapse and effect of metallicity on the stellar winds, you expect metal-poor stars to give birth to larger black holes, possibly. Of course, when we developed this model in 2015, we didn't include several physical processes. We are now trying to implement all of them, starting with peri-instability supernovae. So, what's peri-instability, shortly? When the center of a star develops a very high temperature, let's say more than 10 to the 9 Kelvin or so, then the production of pairs is very effective, and this can effectively remove pressure from the central part of the star, leading to an instability, peri-instability,